Hi everyone, myself N. Arun Kumar from SNS College of Technology in the Department of ECE. In this video, we are going to see about steady state errors. In this PPT, we are going to discuss about steady state errors, classification of control systems, static error constants, static position error constant, static velocity error constant, static acceleration error constants, and example steady state errors. If the output of the control system at steady state does not exactly match with the input, then the system is said to be steady state error. So if you are having the output signal, then it is matched with the input signal. So if it is varies with the output signal, then automatically that may be error occurs in the control system. We have to get the information from input signals, from feedback signals, as well as the control signals of the system functions. It can be happen based on any physical control system inherently suffers steady state error in the response to certain type of inputs. A system may have no steady state error to a step input, but the same system may exhibit non-zero steady state error to a ramp input signals. Classifications. Generally, the steady state errors are based on step inputs, ramp inputs, parabolic inputs, and so on. The magnitude of the steady state errors due to these individual inputs are indicative of the goodness of the systems. Let us consider a unity feedback control system with the following open loop transfer functions. So g of s equal to k into ts plus 1. It can be followed up to the infinity value. So here it involves the term s power n in denominator, representing n is nothing but poles at the origin. A system is called type 0, type 1, type 2 based on the n value. If it is 0, then it is a type 0 system, and 1, 2, it is a type 1 and type 2 system respectively. As the type number is increased, accuracy also improved. However, increasing the type number aggregates the stability problems. And moreover, a compromise between steady state accuracy and relative stability is always necessary for control systems. Here, the steady state error of the unity feedback system has been plotted by using this some graph. R of s is input signal and A of s is a steady state error. G of s is a transfer function. C of s is output system. If it is having any errors, then automatically the C of system will passes to the input signal with the help of feedback signals, and we can get the information by using a E of s, error of the system, so that we can calculate the error of the corresponding transfer function of the control systems. The closed loop transfer function normally represented by g of s divided by 1 plus g of s. Then automatically if we are having more number of transfer function in the system, then automatically it can be added by g of s by using this formula. And next one is the system can be calculated based on the uh, following error signals. The transfer function between the error signal E of s and the input signal R of s is E of s divided by R of s equal to 1 by 1 plus G of s. The final value theorem provides a convenient way to find the steady state performance of a stable system. Since the E of s equal to 1 by 1 plus G of s into R of s, then the steady state error is calculated based on final value theorem by limit t tends to infinity error of time signals. Then it can be calculated based on the system by limit s tends to 0 s into E of s. Then it can be followed by the equation is limit s tends to 0 s into R of s divided by 1 plus G of s. The static error constants are a figure of merit of the control system. The higher the constants, the smaller the steady state error. It can be given in the systems. Then the output may be changed based on positional, velocity, pressure, and temperature. Therefore, in that follows, we shall call the output position, the rate of change of output, velocity, and so on. This means that position represents the output temperature, Velocity represents the rate of changes of the output temperature and so on. The steady state error of the system in the unit step response is given by limit s tends to 0 s divided by 1 plus g of s into 1 by s. If we cancel s, then we can get the final answer as 1 by 1 plus g of s. If it is 0, then automatically the g value will be 0. Then we can get the 0 order system by 1 by 1 plus kp. So like that, all the values has been calculated based on the type 0, type 1, type 2 systems. If the system is step input, then we can have a type 0 system is 1 by 1 plus k. If it is RAM input, then it is a type 1 system. If it is an acceleration input, then it is type 2 system. Also students, how do you calculate a steady state error with respect to input? Step input. The table here, the value shows the Kp value for different systems. Let us consider a value for steady state error for the corresponding transfer characteristics equation as A divided by 1 plus Kp positional error. If it is for a type 0 system, then the error is non-zero. It is called as a finite number and Kp also equal to the gain of the corresponding system. So it has been calculated by using this module limit value. So once we are proposing the limit value based on the final theorem, we can get the steady state error of the corresponding signals. Finally, we can get the error signals by ESS, steady state errors. So like that, we can calculate the errors for any kind of signals. Thank you.